So I'm going to talk about time. That's it's an interesting topic. It's an interesting topic because in software we're really bad at it. In fact, managing time is one of the classic problems that we have. So this one from Melvin Conway: there's never enough time to do something right, but there's always enough time to do it over. That's just an indication of how deeply rooted this problem is. And I want to point out a couple of things here. First of all, this is the Melvin Conway that you may have heard of in the context of Conway's Law. It's the very same Mel Conway, and this is also actually from the Conway's Law paper, which was published in 1968. So it turns out that this is not a new phenomenon, but I want to focus on something else. I want to focus not on our ability to manage the time that we devote to software development. I want to focus on our inability sometimes to deal with the problems of time that is in the software, in our APIs, and how we choose to represent and communicate this stuff. Somebody pointed out, Yves pointed out, names are important for Kevlin. So yeah, I will explain the funny name in this, but I will also, we're going to hit this question about names. This is a really important issue. So let's start with a bit of time travel. So this is from a few years ago, 7 years ago. My copy of Microsoft Visual Studio, 2013. The license will expire in quite a few days though. So this is a kind of curiously precise and suspicious number. It's one of those things when you've been working in software for a while, certain numbers are no longer random. Okay, you've just got used to them. You kind of look at that going, okay, yeah, that's the maximum value of a signed 32-bit integer. For everybody else in the population, the ordinary human beings, they look at that and it's just a random number. For us, it means it's got a significance. That's kind of interesting. We also find these other great edge cases. So a few years ago, I submitted some feedback to Facebook. There's an error. Your feedback will be used to improve Facebook. It hasn't happened yet. Thanks for taking the time. How much time? Well, 31st of December, 1969. I'm going to say that predates Facebook by quite a long way. But that is a really interesting date. And we're going to need to kind of explore a few things to understand what might have led to this. But clearly there's a lot of time travel going on here. This is me as a Time Lord. For those of you not familiar with Doctor Who, it's a science fiction series that dates back, funnily enough, to the 60s. It's been running since then, and various people have taken the lead role. And the title of this talk comes from one of those from one of those doctors, the 10th Doctor. People assume that time is a strict progression of cause to effect, but actually from a non-linear, non-subjective viewpoint, it's more like a big ball of wibbly-wobbly, timey-wimey stuff. And unfortunately, our attempts as developers to bring order to the chaos of time actually don't make it better. They are filled with assumptions. In fact, as he says, people assume. We need to understand this fascinating aspect of knowledge. Assumptions. What is an assumption? An assumption is a very curious piece of knowledge. An assumption is a piece of knowledge that you do not know that you have until after you know that you don't have it. Okay? In other words, perhaps you have an assumption. If somebody said, do you have any assumptions? You go, well, I don't know. And then they tell you something. Maybe it's in a project context. Maybe it's in a real world context. And you go, oh, I had assumed something else. You only discovered you had an assumption when it was contradicted by reality. So at that point, you discovered you have knowledge that is no longer knowledge. And I've likened these to being like Lego bricks. If you've ever stepped on a Lego brick in the dark with your bare foot, you'll kind of know what I'm talking about. If not, then hey, guess what? You know, one of life's new experiences. If you're experiencing lockdown, then stepping on Lego bricks might give you a slightly different perspective on life. But that's the point. If you're walking in a dark room, a child's room, you do not know where the Lego bricks are. So sticking with 1969, let's talk a little bit about how we deal with dates. And we're going to talk about dates and times. This goes back a bit, 1969. To be precise, July 20th, 1969. That would be typically the way that Americans would write it, how I would write it. We might abbreviate it. We might shorten it. And then if we go across the Atlantic, we might also write it like that. But honestly, I have no truck with that. That's just so wrong that it's difficult to express. If I'm in Germany, I might write it like this. I might write the full form like this. I might pad it out to zeros. There is, of course, the one true way of writing it. This is the correct way. Everything else is either less wrong or more wrong. This has the nice benefit of being able to order lexicographically. I actually use this on all of my devices. My kids think I'm weird, but it does have the benefit that everything falls into order. It means that you can represent it as a string or actually as an integer, and use it directly for comparison and for storage at that level. If I want to use the full ISO 8601 form, then I will express it like this. I will include the time and indeed the time zone. Z is for 0 or Zulu time, which is the meridian, or these days we call it UTC. So we're going to come back to times and the dates aspect, but here's another way of representing it. This one is perhaps the least intuitive of all of them. It comes from the C library. We're actually going to see that the C library is responsible and to blame for a lot of problems, many of its assumptions, but also many of its decisions. There is a type in the C standard library, and it has been there since the beginning of time, the beginning of C. C was developed around 1970, late 69, early 70s, and there was a type, time type, and that was held in that you get a time from the time function. You get a time t from the time function. What is the time? It'll tell you. That's held in a header file, time.h. Now, I happen to have a copy of the C standard, the C99 standard. My frustration is I used to have a copy of the C89 standard, but that's gone missing. But here's the C99 one, and it tells us what we can expect of these fundamental types. The range and precision of times representable in clock t and time t are implementation defined. So in other words, we've got no guarantee of what is actually inside there. Is it seconds? Is it milliseconds? Is it some bizarre fraction of a second that we are counting? We have no concept of that. All we know is that it is some kind of numeric type. That's all that the C standard says. Now, many people expect it to be an integer, and they expect it to count the number of seconds since the beginning of time, since the epoch, as it's referred to. This is a different standard. In other words, this is one that's more precise or more committed than the C standard. The C standard is open to many possibilities. The standard I'm quoting here is basically the POSIX standard, which is just a fancy way of saying portable Unix. What you will find is, in fact, in practice, most definitions of time do return the number of seconds since the epoch. And the epoch is indeed midnight, the 1st of January, 1970. So, that is the beginning of time. So let's talk a little bit about this kind of interesting question. That is 0. That is the beginning of time. 1st of January 1970. Now, what happens to times? Do we all walk around? Do we all use, notice that Z on the end. That basically means the meridian time, GMT as it was called back then. What happens to these times? Well, this lovely observation from Anil Dash about a year ago. The natural enemy of the programmer is the time zone. What happens when you apply a time zone to 0? Let us imagine that we do that and that we go back to 1969. Yeah, so here's one theory. One theory is that the variable being used to express the time in this Facebook message was set to 0, and then it was time zone adjusted. Okay, and if it's time zone adjusted to, say, California, I was in the UK at the time, but if it's time zone adjusted to California, then it goes negative, and therefore it will find itself on the 31st of December, 1969. So that's one theory. There is another theory that actually what we're dealing with is -1. In other words, -1 second to midnight, 1 second before midnight on 31st of December, 1969. Where would we get -1 from 0? Well, it turns out that, and this is one of those questions about why it is that people care about how do we do error handling in different languages at different times? That is why, even after all these years, people debate different approaches to error handling. Because in this one, what we've got is the idea that time t minus 1 is the indicator for an error. It's not actually a valid time at all. So therefore, as you can see from the standard, it says, yeah, the value -1 is returned if the calendar time is not available. That may mean that your clock is not set. You know, it is possible to have a system that does not have a set clock. It is also possible to have a system that does not have a clock. That is, I've worked in embedded environments before where that is also the case. It is also possible that you're asking for a time that cannot be expressed. So in other words, the phrase not available is really broad. So that's one of the other possibilities. And actually, I think it might be the more likely one rather than the time zone one, but I have no way of knowing. But this does also give rise to another thing. You may recall that I said this before. Actually, there is no requirement on a POSIX system that you are able to represent anything before the 1st of January 1970. So in other words, this might end up being -1. There is nothing that happens before. You are beyond the event horizon of time. There is no south of the South Pole. There is no earlier than the 1st of January 1970. So that may also be an interesting consequence. Again, an assumption there. If that assumption is true, then it does actually mean that I was personally I was born before the beginning of time, which kind of makes you sound kind of cool and immortal. So let's flip to something more contemporary. So that's all C, that's 1970s and all the rest of it. And I'm guessing many of you probably don't work in C. I occasionally work in C. I also occasionally work in C++, which brings a lot of that baggage with it. So perhaps we should be free of this and let's talk about something more contemporary. Let's talk about Java. So this is Java is a child of the 1990s, but still going strong. And actually, if you look at the top 10 programming languages, so C and C++. But I recently finished editing this book with Trisha G. This was kind of a lockdown baby that we wrapped up in about May, and it was published hard copy in June. And one of the pieces that I wrote for it was actually on time. To be precise, the date class that exists in Java. And it is a truth universally acknowledged that a single programmer in possession of the belief they understand dates and times must be in want of a code review. Put another way, date time handling is harder than people expect, even when they're expecting it. No matter how hard you think it is, it's going to be harder. Just to reveal some more assumptions. So this is Miguel Cervantes. Basically the great Spanish author, and he died on the 23rd of April in 1616. This is a statue of William Shakespeare, okay, great English playwright. He died on the 23rd of April, 1616. Uncanny, what a coincidence. It is also, by the way, the reason that the 23rd of April every year is International Book Day. It's a remarkable coincidence, and occasionally you'll find people going like, oh my goodness, this is spooky coincidence. Yeah, it's not so spooky. It actually shows what a mess we've made of time. It turns out we can make a mess of time without computers. So here's the baseline assumption. 365 days in a year. Well, it doesn't work out like that. Earth is not tidally locked to the sun. There's no neat relationship between the Earth's rotation and its orbit around the sun. There's only one planet in the solar system that has that, Mercury. It has a 2 to 3 relationship between its year and its day. But that's it. There's nothing interesting. It's not like the moon is tidally locked to the Earth. We have no relationship on this planet to the sun when it comes to rotational period. In fact, of course, it's a mess. This is roughly what it is, which is a very awkward number. And humans are not very good at counting this. So every now and then, what we do, there are lots of different calendar systems. I'm just going to refer to the contemporary Western calendar that has been used and is official in every country. Other calendar systems are absolutely fascinating in how they have dealt with this. Lunar calendars are not the only alternative as well. There's a lot of interesting stuff. The way that this is resolved is that every now and then we will throw in a 366th day, an intercalary day, as it's called, an intercalary day, just to even things out. Now, historically, the Romans were the first on this. We get to blame the Romans for quite a lot. They were the first on this. So here's a little piece of groovy code. This is your standard Julian calendar named for Julius Caesar. Okay, so you get a Julian leap year once every 4 years. That means we've got an approximation of around 365.25. That's not bad. That certainly allowed the Romans to kind of adjust their years back and reclaim that. But it's still quite a long way off what we need. Over the years, this accumulates. It means that our seasons will start to drift in terms of our perception. So, Pope Gregory, the ninth, I lose count of all these popes and kings, and the Gregorian calendar came in with this algorithm. Okay, so instead of every 4 years, it's every 4 years unless it's every 100, with the exception of every 400. I think this is always a great teaching example because people find it very difficult to express because humans are not logical. We are trying to combine an or, and a not. That's just too much for people. That is way too much. That's outside our comfort zone. But what does that give us? You know what? That's not bad. The previous one was about the actual one is about 365.2422. So we don't need to adjust this. We might need to adjust this around the year 3200 or so. But honestly, I'm not going to worry about that one right now. We're good. So obviously what happened is when this was introduced in the late 16th century, not everything happened at once. It turns out that there were different calendars running concurrently within Europe. And in fact, it was one of the slowest rollouts in history. I think Turkey was the last country to go. Basically, it was around 350 years from when the Gregorian calendar was introduced to when it was actually formally adopted by all countries. Which means that 23rd of April, 1616 in England was actually the 10th of May, 1616. So this is the curious thing that although Cervantes and Shakespeare died on the same date, they did not die on the same day. And this is where the words start getting messy. It's just like, wait a minute, I thought the same date was the same day. No. It was the 16th of April in both cases, but they were actually different days. They died a couple of weeks apart. And this is where we start caring a great deal about language. In Domain-Driven Design by Eric Evans and the Domain-Driven Design movement these days, there's a lot of care about what is the vocabulary of our domain. We're trying to create a system of thinking and concepts. So we're gonna play a little game here. Okay, it's the end of the day. Let's just see how you do. Let's look at Java and let's look at JavaScript. What does the date class represent? Right, is it A, a calendar date, B, a day of the month, or C, something else? Now you're thinking, okay, how else can I interpret date? And yeah, it's something else because the other two would be too obvious. It's a date time. So it turns out that it's not a date. It's called a date, but it's not a date. It's called, we would conventionally call that a date time. And the date also contains the time. That's very unusual. That's not how we use it in English at all. So this was a really bad piece of naming. We're going to blame Java for that one because JavaScript borrowed it from Java. But it's also not just a date time in the way that you or I would conventionally think of it. It's a date time in milliseconds. Okay, so we're off to a really bad start here. In the date class, what does the getDay method return? Okay, so when we say day, do we mean day of the week? Or do we mean the day of the month? Okay, so today is Tuesday, and it is also the 24th. Both of these would say, what day is it? We might say, what date is it? But yeah, or is it a day of the year? Okay, so that is also a possibility. Sometimes we care about the day number of the year. That's less common. We're more likely to talk about the week number of the year and the day number within that. So in the context of this stuff, it turns out the answer to this is getDay returns the day of the week. Okay, that's not too wild. We can get behind that, but we're going to come back to getDay in a little bit. But here's the interesting question. If you've got a class called date, and you have a class called date, and it has a method called getDate, what does that mean? Now, this is one of those ones where you would definitely code review this one, but does this return a calendar date? Or does it return a day of the month? Or does it return a date time? Because clearly the name date means date time. But we've established that. The class date is a date time. It's not a date. It's a date time. No, we use this one. So rather than using clear terminology like get day of week and get day of month, Java keeps you guessing. Okay, and JavaScript made no effort to fix this. So what we discover here is this classic observation from Phil Carton. There are only two hard things in computer science: cache invalidation and naming things. So, yeah, there's actually more hard things. Based on get date, what day of the month is it today? Is it 24 or is it 23? Are we zero counting or is it something else? The good news is 24. Okay, so there is a correspondence between the domain of the user and the real world and the way that it is actually expressed here. Okay, so they might have got the words wrong, but they've got the numbers right. Based on get month, what is the current month? Is it 11? That's how I think of November. Or is it 10? Or is it something else? I have some bad news for you. It's 10. There are two hard problems in computer science: cache invalidation, naming things, and off by one errors. It turns out that although we conventionally use 1 through 12, the C library chose to count from 0. And therefore, Java, which is obviously completely source compatible with C, also decided to choose 0. So in other words, Java, when it was introduced in 1995, did not fix this problem that was a well-known problem in C, that people get this one wrong. And neither did JavaScript, which is also obviously source compatible with Java. So when people sort of say, well, it's because Java did this, I don't get that, because these languages are not source compatible. There's no reason they have to do that. There's no reason you have to carry on somebody else's mistakes. Now, I'm not saying that zero counting is bad. I think zero counting is really good for a lot of things. The issue is you've got two choices, 0 or 1. Don't choose both. If you are counting your days from 1, then you're also counting your months from 1. It does not make sense to have both. Okay? This is a terrible piece of API design. If you think about it as a user interface design, it's equivalent to having your OK cancel on one screen this way round and your OK cancel on another screen the other way round. Well, sorry, cancel OK. You're asking for trouble. People get the stuff wrong. I remember in the early 2000s, I ran a workshop. It was an agile workshop for a company in Ireland, and we ended up. People started using the date class, and all of the agility just disappeared from the room. Everybody started getting mistakes because so many people are unfamiliar with how to use the date class. Everybody was happy with Java as a kind of easy language to work with, to express their object-oriented ideas. But the minute we hit this terrible class, date, suddenly everybody slowed down. So we actually banned the date class from that workshop because it was causing too many problems. But let's go back to this counting question. So it kind of seems obvious that we have our months as they are. It's roughly based on the lunar cycle, but approximated. I have a couple of blog pieces on Medium that are a little bit more about calendars and things. And if you're familiar with the month names, you may know a few things such as, and you'll see this across many European languages, there is a representation of these months are all very, very similar. It's actually one of the points that you can go across many European languages and go, wait a minute, I know what month that is without necessarily knowing the language. But we have various things. So July is named for Julius Caesar. August is named for Emperor Augustus Caesar. March is named for Mars, the god of war. January is named for Janus, the god of beginnings and endings, a god that looked to the past and to the future. Now, it seems really obvious that January is the first month of the year. Sadly, that's not the way it works. March is actually the first month of the year in the Roman calendar. The Romans do not, and indeed many other cultures, do not have the same anchoring and perception of how the calendar works that we do today. We have a very narrow view. The Romans loved festivals. And so, yeah, sure, they had festivals around. They felt that Janus was a point towards where the day started getting longer. It was a reasonable time. It was about a week after the solstice. And so therefore a sense of new beginnings. But actually March was when spring was around. That was technically the beginning of the year. Now, when you understand that, you also understand something else. This is how they would have counted it. Or if you're going to write it, if you're going to be Roman, let's do this in Latin. Which is kind of interesting because it makes an awful lot of sense when you suddenly realize that if you've never wondered this before, I now have an answer for you. Why is it that September, October, November, December, 7, 8, 9, 10 refer to months 9, 10, 11, 12? It's because it's an off by 2 error. It basically, what happened is they clearly didn't have enough emperors or gods. Well, they'd had actually plenty of gods, but nobody felt that one of those months deserved a god's name or a particular emperor's name. Okay, so you kind of get this problem where they ended up hard coding this. You can just imagine the programmers. These months don't have any names. Just number them. But isn't it bad practice to hard code numbers? Oh, it'll never change. Nobody will ever change this. Just hard code them. And that's what you've ended up with. You've ended up with months 7, 8, 9, and 10 being months 9, 10, 11, 12. There is a lesson there for programmers from 2,000 years ago. Okay, let's get back into the questions, because obviously it can't get crazier than we've already seen. Based on get year, what is the current year? Is it 2020? Is it 2019? Or is it something else? It's something else. The current year is not recommended? One for the history books? Yeah. One to forget, definitely. It's actually 120. So, yeah, we get to blame C for this. In fact, in JavaScript, get year is deprecated. There is an alternative called get full year, which will give you the right answer. And it was the classic idea that this stuff, we're going to blame C again. All this stuff was a shorthand. It was like, oh yeah, 2-digit dates. If you think about it, this would have been 1970. It was 50 years to the turn of the century. 2-digit dates, yeah, we can do that. I read a piece a while back that actually said one of the biggest problems in the 1960s was that a number of systems used a single digit for date representation. And we may have worried about not being able to see the millennium coming, the end of the century coming, but it turns out in the 1960s, people really didn't think their software would last very long. And actually left and actually had the year 1970 problem in a few systems. So there's a lot of stuff here that we get to blame C for. And I'm not going to say that C was bad in this. The problem is that C, nobody ever tried to fix it. Nobody ever said, you know what? We need to replace this, especially, and I am going to blame anybody who has ever developed another language or another library on top of C, which is pretty much everyone. There was no reason to continue this. Just because somebody else makes a mistake does not excuse you from not fixing it. So let's go and dig into a couple of other assumptions here. Going back to Java and to JavaScript. The POSIX time function returns seconds since the 1st of January 1970. That's something I mentioned earlier in the talk. So the date class has a GetTime method. What does that return? Seconds since 1970. Yeah, that would make sense. Milliseconds since 1970. That would make less sense because we're patterning it after the Unix or the C stuff or something else. Turns out it's milliseconds since 1970. So in other words, where we have something of the same name, time, it actually does something very different. But there's other conventions we want to explore. Today is Tuesday. What does getDay return? If you remember, we established that day is day of the week. It's not day of the month. It's, we're clear on that. So what day is Tuesday? Is it 1? Is it 2? Or is it 3? Yeah, this is an interesting one because part of this is a kind of convention of, do we count the beginning of the week from Sunday or do we count it from Monday? This is an interestingly cultural one. A lot of people will say, you count it from Monday. And in fact, we actually see this, most languages in Europe follow a very similar pattern of naming. So Monday is the day of the moon. So we end up with Monday in English and Montag in German. But we also see in French, lundi, that's moon day. So we have that. Wednesday Woden's Day, Thursday, Thor's Day. Okay, so we're borrowing here from the kind of like the Old Norse gods. But actually, it also works if we realize that these also translate across different pantheons. So if you like, Thursday in French is jeudi, which is actually a reference to Jupiter, who is kind of the correspondent. He was throwing lightning bolts, so was Thor. So there's a kind of a correspondence across these. But some languages don't do this. So here's Lithuanian. Now, I don't speak Lithuanian, but I was in Lithuania last year, and I was walking past a shop, and I suddenly saw the shop had its opening times and days. And you don't have to speak Lithuanian. Lithuanian's got Lithuanian as a language. It's an Indo-European language. It's almost one of the purest Indo-European languages in the sense it hasn't changed a great deal. Okay, we have a Lithuanian speaker. Excellent. But just looking at it, just as somebody who has an interest in languages, you're going, so apologies for pronunciation. Prima DNS. I'm looking at that going like prima, that's like one. And Trecia DNS, again, pronunciation is not my strong point here, but that looks like 3. Penta, that looks like 5. Penta. Sesta, that looks like 6. In other words, these are day numbers, and they are numbered literally 1, 2, 3, 4, 5, 6, 7. Day 1, day 2, day 3. So that solves the problem. Monday is day 1. Yeah, not so fast. Turns out my mother tongue, not that I speak it well now, but my mother is Brazilian. My mother tongue is therefore Portuguese. Portuguese also numbers the days. It numbers them differently. The weekends get their own name, but Monday is segunda-feira, second day. Third day, fourth day, fifth day, Friday is sixth day, sexta-feira. So in other words, we see this kind of numbering system. You can see it's a political minefield. How do we choose to count the days? Yes, and as somebody pointed out, days of the week from Monday to Saturday also number 1 to 6 in Chinese, and also, if I remember correctly, Chinese numbers the months. So for months, it's a lot easier. Days, there's an open question here. So you can see there is a political and linguistic minefield. Today is Tuesday. What does GetDay return? For some of you, you're going, oh, okay, I've got this. This is nice. Oh, yes, actually, interesting point there about Chinese. Sunday is the day of the heaven. Let me just point out something weird about Portuguese. Sunday, domingo, that's the Lord's Day. Saturday, sábado, that's the word for Sabbath, which in Judaism is the Lord's Day. So therefore, the word Sabbath is sometimes used to mean Sunday and sometimes used to mean Saturday. So the days are actually ambiguous in translation. So good news, Tuesday is 2, okay? That's great. Obviously, that doesn't really work in a lot of languages. And you might be thinking, I see, that is because it's numbered like this. Guess what? You'd be wrong. It's numbered like this. Sunday is the first day of the week, but we're counting from 0. So whatever assumptions you have, you can be sure that they will be broken. And this is one of the places where they get broken. But although it sounds like I'm being harsh on C, I did say we can't always account for some of those decisions. We can question those decisions. We can say, you know what, it's in the early days of computing. I don't think people realize the consequences. I don't think anybody realized how influential and long-lasting C would be. One of the things we can say about C is that it is incredibly thoroughly specified. It is one of the most precisely specified languages. I've been involved in language standardization, and C is like one of the kind of like the archetypes. It is, although it will tell you precisely what you can and cannot expect. Okay, that doesn't mean all the behavior is well defined, but you are told exactly what is and is not defined, which is natural. This is a language whose original raison d'etre was portability. So therefore, it makes sense that it's going to end up with a very tight specification. So here's the data structure that we get to blame for a lot of this stuff. I want to pick on another thing. We've kind of looked at a few things, days and years and things like that. Let's just anchor on this little one here. The number of seconds, 0 to 60. Just before continuing, Angles asked, were some of C's mistakes also inherited from other languages and systems, or was C really the precursor of all of these decisions? It was, to the best of my knowledge, the precursor of most of these decisions. A lot of mainframes took a very different approach. So there were lots of alternative approaches, but yeah, C was kind of the point of origin for a lot of these. And to answer the question that's just popped up, it allows for positive leap second. So basically, since 1972, we occasionally add in a leap second because it turns out that the Earth's day is not precisely 24 hours. It's not precisely 86,400 seconds long. On average, it is, but it drifts a little bit. It's now at a level of sensitivity where occasionally we may need to add a second, and that's not something that can be easily anticipated. So the idea of leap seconds post-dates the introduction of C and actually follows the beginning of time. So this is the 1999 standard. I'm going to reach your assumption in a moment, Johan. I want to go back to the 1989 standard, the original C standard. This one always fascinated me because I remember reading this and going, well, hang on. Why? It was originally 0 to 61, 2 leap seconds. It's like, what? Now, one of the things you need to know is that we'll get to TMY day in a moment. You cannot have more than 1 leap second in a day. In fact, the way that it's standardized is that you can have at most 1 leap second in one day. And there are only 2 days where leap seconds can get added on in the year, the 30th of June and the 31st of December. And those would normally be the last second of the day. So, you could some years are longer than they are. And the fact that 2020 has been a leap year probably makes, we don't have any leap seconds this year, but honestly, this has been one of the longest years I remember, and not just because of the leap day. But for some reason, C89 accommodated 2 leap seconds. Now, this is an interesting one because this is kind of like an accidental piece of future-proofing. Just in case maybe we need an extra one, it's just like, nope, there was no reason for that. And what I discovered is, digging around, is in the 1988 draft of the standard. I found the 1988 draft of what became the 1989 standard. Actually, it was a late edition. Originally, they were going to standardize for just 1 leap second that you could include in a day. And then obviously somebody at the last moment panicked and said, oh no, we need to generalize, we need to future-proof it. And I'm sure that everybody here is just like, oh yeah, future-proofing, that always works. Yeah. So in C99, they said, no, we're just going to take that back. Now, a lot of systems no longer, so the leap second is an interesting one because it means that it potentially means that systems diverge. The way that some systems handle it, so Google handles this by, and an increasing number of systems handle this by using leap second smearing. Rather than adding a second, so that you end up with a minute that had 61 seconds at the end of the day. What they do is on the day that you're going to add a leap second, is they just kind of slow everything else down a little bit. All of the days are like 1/86,401th of a second slower. And so by the time you reach the end of the day, you've actually done all 86,400 seconds, but it took 86,401 seconds. Unless you are absolutely needing of atomic clock time, and indeed I would say the New York Stock Exchange uses an atomic clock time. New York Stock Exchange stamps its times with respect to nanoseconds. But apart from that, for most people, having that extra second, having it smeared out over the day doesn't make a big second. But I love this classic from XKCD. Why do the clocks say it's 3 a.m.? Well, adding an extra day creates too many glitches. So we're just running our clocks 3.4% slower during February to avoid leap day irregularity. It's a lovely way of doing it. Now let's go back to leap seconds. The last leap second we had was 2016. It turns out that the number of leap seconds that we need has been slowing down. And this observation was made. The absence of leap seconds has the advantage that leap second bugs don't get tickled, but it also has the disadvantages that timekeeping code might rot and new bugs or regressions can be introduced without anyone noticing. Yeah, let's go back to that other assumption that was highlighted in the chat. Positive leap second. Interesting. We are actually now running the risk that the day may get shorter. There may be a year where we actually need to have a negative leap second. There has never been a negative leap second. And if there is one, everyone who deals with NTP or kernel timekeeping code expects that this will be an appalling shit show. That's technical terminology. Okay. Nobody ever accounted for this. Again, that amazing assumption, because we are so used to adding leap days, and this idea back in the early 70s based on measurements in the 1960s is that, yeah, it's a little bit of slowing down thanks to the motion of other planets and so on. We can't fully predict it, but we probably need to add leap seconds. The idea of retracting a second did not cross anybody's radar. We shall see what happens to that in the next decade. Right, let's go back to this. 0 to 365. We are counting year days. Remember, we keep jumping between ones and zeros, okay? We are counting the number of days since the beginning of the year from 0. So therefore, we can accommodate 366 days. Surely, nobody's going to do anything stupid like add more days in. Yeah, right. Okay. Let's go back in time. Let's go back to the 4th of October, 1582. Let's go back to the Vatican. So this is the year, and this is actually the date after which the Gregorian calendar was introduced. Basically, in Rome, there was no 5th of October, 1582. It went straight to the 15th of October, 1582, and indeed did so in a number of other countries, Catholic countries, but most other countries followed slowly after that. And some took a lot longer. So in Britain, it wasn't until 1752. 2nd of September was followed by the 14th of September. Okay. And in a number of countries, so basically different countries adopted at different times. I think Denmark was around 1700 or so. Sweden and Finland, it was 17th of February, 1753, was followed by the 1st of March, 1753. But here's where the dirty secret comes out. Although moving from Julian to Gregorian calendar caused a lot of people, there were a lot of differences. In fact, in the Holy Roman Empire, you could travel across Germany and you would change date multiple times depending upon whether the kingdom or principality that you were in was Catholic or Protestant. Because if it was a Catholic principality, then it would be on Gregorian. But if it was Protestant and Lutheran Church, it would be on Julian calendar. So you could actually move through time as you cross the country. Sweden did not. This is not the first time Sweden tried to change their calendar. Sweden, of all countries, has the most creative approach that I've ever encountered, and it was absolutely disastrous. What they decided was that they would not move from the Julian calendar to the Gregorian calendar all in one go, like every other country was doing. Oh, no. What they would do is they would not have any leap years for 40 years. So basically, they would not have a 29th of February for 40 years. And the idea was slowly, if this is Julian calendar and this is Gregorian calendar, slowly over a 40-year period, they would drift from one calendar to the other. This is kind of like a really slow motion geological ballet. Okay. So basically Sweden would be wrong with the two calendars. So the one way of looking at it is that they're doing a slow migration. The other way of looking at it is actually they're wrong for 40 years. There is no other calendar that matches what they're doing. And this was the plan. However, no plan survives contact with the enemy. This is an old military saying. What happened, and this is actually the problem, what happened is that in 1704 in Sweden, they had a 29th of February. In 1708, they had a 29th of February. Why did they do this? What happened? So they were still wrong, but now they were differently wrong. What happened is that they were busy fighting a war, the Great Northern War against Russia and its allies. And it turns out that changing calendars whilst also conducting military campaigns is a really bad idea. Particularly if you go back a few centuries, the whole idea of telling your generals, by the way, we need to send reinforcements here. Remember, everything is much slower than it is these days, and we're going to plan for this on this date. If not everybody's working on the same date system, you could end up with some very embarrassing episodes, like turning up to a battle a day late. So really, they didn't concentrate on this whole idea of let's change the calendar as well. So I can't remember which king it was. It was a Charles. But the king at the time said, look, this is ridiculous. Let's go back to the Julian calendar, which they did in 1712. They said, right, let's go back to the Julian calendar. And then in 1753, they did it all in one go. Okay. So how did they do this in 1712? Because they'd already taken on 2 leap days. They did this in 1712 by having a 30th of February. And here is a document I dug out from the Wiki Commons showing this. There's Februarius, and there is day 30. This is an official Swedish piece of legislature. So basically, what we see is that in 1712, Sweden had 367 days, which completely breaks that assumption in the C Library. So it actually turns out that the C Library cannot represent accurately dates in the Swedish calendar and still be conforming as a C implementation. You have a choice, either correctly represent the Swedish calendar or correctly represent C. So one might say C is incompatible with Sweden. You will be delighted to know that in 1967, when Sweden decided to change from driving on the left-hand side of the road to the right-hand side of the road, they did not do it slowly over a period of 40 years. They decided, you know what, I think it was Dagen H. It was just like, right, we've got basically this, we've got a few days, here's the cutoff point, everybody stop, change over, and then bring all the relevant classes of vehicles back online over a period of a few days. They did not do it over a few years. So that kind of brings us to the end. And the observation that is known as Anderson's law, I've yet to see any problem, however complicated, which when you looked at it in the right way, did not become still more complicated. And as I wrote in a blog, if you think you know everything you need to know about date time handling, you are almost certainly wrong. If you think you don't, you are almost certainly right. So thank you very much